Let's chat a little more about linear transformations. So you might recall linear transformations have additivity and scaling, or you can put those together and they're linear if they satisfy that shortened condition. So let's talk about two key linear transformations. If V and W are vector spaces over a field, we define the identity transformation, IV from V to V, as just IV of X equals X. And sometimes we even functionally write I. So like I from R2 to R2 would simply be the map that takes I of AB to AB, right? Pretty straightforward. And there's the zero transformation, T0 from R2 to R2 would be, or I guess technically I should have W there. It could be whatever space you want. Let's make it R3 just for the fun of it. T0 of AB maps it to 0 in here. So that could be 0, 0, 0 if that's my codomain right there. Right, so you can go anywhere, but the point is that everything maps to 0, and they satisfy these rules in the sort of silliest way. Well, of course, if you have the identity, you can do nothing to the sum, or you can do nothing to the elements and then sum them. And of course, if you map this to 0, or you map this to 0, multiply it by something so it's 0, and add 0, you get to the same place. So those are pretty straightforward. Now, here's an interesting thing. Remember, we have a map. There's the domain, and there's the codomain. There are some key subspaces. Now, I'm going to define a set, and the theorem down here is going to say that that set is a subspace. But have a look here. The null space, or the kernel of T, is n of T, which is equal to elements of the domain such that T of X equals 0. So the null space lives in the domain. It's a subset, and we'll prove that it's a subspace of the domain. The range, or image of T, R of T, is T of X. Notice those live in the codomain right here. And you might be more familiar with the term range there. Well, the range is the points that actually get hit, right? The codomain is just what's there. There's no guarantee that you are onto, that you hit every element in the codomain. The range is what actually gets hits. So let's look at an example real quick. What would be the null space? And this is the video. This is the example from the first video. What's the null space of this transformation? Well, it's the set of, I guess, AB. Remember, in the domain, the null space is in the domain such that T of AB equals the 0 polynomial, right? Well, in other words, it's the set of AB in R2 such that, what was the definition of this? I could just say AX squared plus 2B equals the 0 polynomial. Well, if you think about that, how can you have a polynomial with some coefficient times x squared and some constant equal to 0? The only way you can do that is if A is 0 and B is 0. So the null space is, in fact, a subset and the trivial subspace in a subspace of the domain. What about R of T? That is a subset of the codomain. It's the set T of A, B, such that the pair AB is in the domain. Anything in the domain fired over to the codomain. So what could I do? I could again take the definition of linear transformation. It's AX squared plus 2B such that A and B are any real numbers, right? So you could leave it like this. This is technically accurate, but it might be better to observe, hey, I can have any coefficient in front of x squared that I want. And if this is any real number to B, you can actually have it be any number you want. So that set is a subset of the codomain, and it turns out it's a subspace. So we'll finish this up by just pointing out that with a linear transformation, both the null space and the range are subspaces of V and W respectively. Respectively means this is a subspace of V, this is a subspace of W. So our proof will use, not surprisingly, the subspace test twice, using the subspace test. One, remember the first condition of the subspace test is that 0 has to live there. So we're starting with the null space. Well, T of 0 equals 0, right? That's a condition. So that's the very definition of 0, this element of the domain, being in the null space. Good, taken care of. Okay, 2. Let's pick two things in the domain. Sorry, let's pick two things in the subset. Let x1 and x2 be in the null space, okay? And where do we want to end up here? Well, we want to end up with, therefore, x1 plus x2 is in the null space. But let's just think about what this means. What's it mean that those two things are in the null space? It means t of x1 is 0 and t of x2 is 0. You can just consolidate that to one line. So, but then what do I really want to say? I want to say this means t of x1 plus x2 is 0. Well, what is this? And here you get the bread and butter of every linear transformation proof, right? This, by virtue of it being a linear transformation, is t of x1 plus t of x2. By assumption, that's 0 plus 0, and that's 0. And that's the very definition of being in there. 3 is going to go very similarly. I've got to pick something in the null space, and I've got to pick a scalar. Let me pick my scalar first. And x being in the null space. And you know what that means. That means t of x equals 0. And I'd really like to do something here, and I'd like to end up with what? I'd like to end up with cx is in the null space. What does that mean? That means t of cx is equal to 0. Well, I don't know that yet, but by linearity, I know that equals c times tx. I know tx equals 0. And I know 0 scaled by anything is still 0. So I really do know that it's a subspace. Therefore, subspace. Similarly, with R of t and the subspace test, let's see, 1. Now here, I want to show that the 0 in the codomain is in R of t, right? So what does that mean? That means 0, well, I know that 0 is equal to t of 0. Oh, well, that means it's by definition in R of t, right? R of t is exactly the things that can be written as t of something, right? 2, not a big shock. We're going to pick two things in the range. Let y1 and y2 be in the range. What does that mean? So choose x1 and x2 in the domain such that t of x1 equals y1, right? If it's in the range, there's got to be such an x1. And t of x2 equals y2, right? Where are we trying to end up, right? If there's any justice in the world, we better end up with, therefore, y1 plus y2 is in the range. What's that mean? It means we need to write y1 plus y2 as t of something. Well, gee, I can't write it as t of something right away, but I could write it as t of x1 plus t of x2 by what I have. But these are linear transformations. What a shock. So we'll say the sum of the outputs is the output of the sum. And in fact, that's the definition of being in there. Last, let C be in the field and Y be in the range. You can guess where we're going here. So what does it mean to be in the range? It It means I can choose x in the domain such that t of x equals y. I'd really like to say here, I'd like to say cy is in the range, but in order to say cy is in the range, I have to write cy as t of something. I can't do that yet, but I can say c times t of x is equal to that, since y is equal to t of x, and by linearity, that's t of cx. That's the very definition of this being here, therefore subspace.